exercise 6, number 3. This time a little bit, well, more than just taking the derivative of a term. This is quite a nice exercise, as I think. I like it because it contains a certain, you could a seeming contradiction, which is not a contradiction at the end. In the end, it must be taken away, of course, in a certain way. Now let's look at the original setting where this term is given, and the question is simply to find the angle of inclination, as it's given here, angle of inclination, under which the graph of this function meets the x-axis. So now if you interpret this correctly, you can conclude that there is obviously just one single value of x. So that this term would have just one simple zero, sort of a root of this term. You know that root is sometimes used as a synonym to say zero. Well, anyway, it's fact. If you can, of course, you can use Geogebra tools, whatever, again, to make a plot of this function. You will find that it has a simple zero somewhere, and so the answer to this question will be the, well, taking the slope of the tangent at this position and then just transforming this using the standard formula with the tangent of alpha as the inclination angle being equal to the slope. So that's just steps behind. But then basically you have to find this zero first. And now it turns out by trying and setting this term equal to zero, the result will be, at first sight, it will be a contradiction to the domain of this function, which has two definite and two distinct definition gaps. Now let's start out. Well, let me look. There's something in the chat. Yeah. Okay. See you. Let's look here. What are the definition gaps? But first of all, we may never divide by 0. So obviously there's a gap at x equals 1. You see? So this is what I have to exclude. And the other one, which is contained here in this divisor, will be -1. So that's quite obvious. Also, quite interestingly, both of these gaps are even contained once more inside this quadratic denominator term. So there is several reasons to say that this function is not well defined as well for x equals -1 as for x equals 1. So we have to exclude these both values. Now, but on the other hand, just ignoring this or accepting it and then finding the zero of this function where it meets the x-axis means we have to, now let me reactivate this, we have to make this, set this expression equal to 0, and then, in the best case, find a fractionless version of this equation. So this is standard technique, solving a fractional equation by making it fraction-free, getting rid of the fractionals. Okay, so the fractions. So what? But now it's a good idea to cross out this denominator term and replace it by a better, representation. I hope you see easily what I'm doing here. I recognize that this one is due to the third binomial formula where I can split it up to be x minus 1 in parentheses times x plus 1. You see, x squared minus 1 equals x minus 1 multiplied by x plus 1. That's quite easy. And this is what I did. But then I have another factor of x plus 1 parentheses. So I get x plus 1 in parentheses squared. So this is a better representation because it contains linear factors only. This is what will help us to proceed solving this exercise. Look what happens next. Now, I will multiply the whole equation through with its, you could say with its full denominator. This term contains everything we need because x minus 1 here is already contained here. So that's what we take. We take this whole equation times x minus 1 and times x plus 1 in parentheses squared, thereby stating that x should be unequal to 1 and unequal to -1, of course, in order not to multiply the equation by 0. Otherwise, we would lose its information. We would get 0 equals 0, which is not what we want. Okay, you see what I mean. Nick, because I see your remark, can I use partial fraction to simplify? Yes, you can always do so. Now the question is, is it efficient? It will work, I promise you. You can just, it's even a good idea. You can decompose this expression into partial fractions to simplify it, but it might take you too much time in order to be efficient. Try and do so and find out yourself, okay? I would say it's easier because we just bring this to non-fractional form, which I do right now. You see what I'm doing? Multiplying this whole term. I see that with the left fraction here, this x minus 1 cancels out. What stays is 1 times this parentheses squared, which is x plus 1 in parentheses squared, minus now the other one, of course, the whole denominator disappears, and I stay with negative or with minus 4x. And this should be equal to 0 still, because the 0 times something is still 0. Now, solving this is quite nice because this is first binomial formula where I can explicitly say it equals x squared plus 2x plus 1. But then I have to subtract 4x, which means the whole expression transforms to one which resembles the second binomial formula. That's quite interesting because now altogether I get x squared minus 2x plus 1. I think this is easy to see, right? So this can again be transformed back in parentheses to be this time x minus 1 and then squared equals 0. And now it's almost solved because we can draw the square root. We don't even need a case distinction because square root of 0 is 0, plus or minus 0, no matter. So we get x minus 1 equals 0, and this means x equals 1. Actually, truly speaking, or honestly speaking, this would be a double solution of this equation, but it turns out in the end, it's just a simple solution due to a certain removable definition gap, which I know you could say this is a postulate. I just recognize that something's wrong here because you see that the 1 is a definition gap of our function, but if it's at the same time, if it's a 0 of this function, and honestly speaking, there must be at least 1 0, otherwise the exercise would not be well defined. It is most probably, it should be the case that we have a removable definition gap at x equals 1. And this is, of course, this is a little bit, well, and this is not a proof for it to be removable, but we can prove it. So the best idea would have been to simplify this whole function expression right away. And so this is what I do afterwards. Now, look at this, what I'm doing. Draw these two fractions together using the main denominator, which is x minus 1, you see here, times x plus 1 in parentheses squared. And then I just expand my left-hand fraction just using x plus 1 in parentheses squared. You see, expanding it by multiplying this term in the denominator and in the numerator. So it stays in the numerator, it gets me x plus 1 in parentheses squared. Then I take minus 4x unchanged. You see what happens here is the same thing again as here. It's that this gets transformed to be sort of the second binomial formula. And now I see that I can cross out one of these x minus 1 factors of the numerator against one of the denominator, the one in the denominator. And this is the moment where I'm successfully removing this removable definition gap because it's gone away below. And now you see what remains is much nicer than the original form. This is a fraction of the sort x minus 1 over x plus 1 in parentheses squared. This is very easy to be analyzed. It's a properly fractional function, right? It's a proper fraction because the numerator grade is 1, while the denominator grade is 2. Okay, it means on the outside it's damped. It approaches 0 on both sides. Approaching infinities. X approaching infinity plus or minus the whole function approaches 0. That's what I mean, because it's properly fractional. So it has the x-axis as a horizontal asymptote. It also has a clearly a vertical asymptote and a true definition gap at -1, which is twofold. So multiplicity 2 means we have a pole at this position with no signature change. Look here, this is the pole, here it is. But we also have a simple 0 at x equals 1. So now this obvious, or this supposed contradiction which we had has disappeared, right? And as you can guess, there will be rather a flat curvature. Well, the curve will be rather flat, and also this inclination angle alpha, which we're looking for, will be relatively small, even in the classical degree measure. Anyway, after removing the gap, we can say that the domain now equals real numbers without -1. This is the only remaining gap. Now look, had I used this expression from the start, it would have been much easier to find the 0, of course, but latest at this point, it's a good idea to use this expression instead of the original one in order to find the first derivative. We need the first derivative. Why? Because we have to insert our 0 into the first derivative in order to calculate the slope of the graph of our function at this position. So this is a good good opportunity to use the quotient rule again, or the ratio rule of differential calculus, which I'm doing. I'm using the scheme that I take the denominator term squared. Now, since the denominator term is already x plus 1 in parentheses squared, I have to take x plus 1 in parentheses power 4. Here, you see it in black color. And then I use the scheme, take numerator prime times denominator, which is, since the numerator prime equals 1, it's just the denominator term here, x plus 1 in parentheses squared, then minus the other way around, so minus the numerator term x minus 1 times the denominator term prime. Okay, so this must be differentiated now, which I do by using the chain rule. 2 times these parentheses, and that's it. 2 times x plus 1. You see, we don't have to post differentiate because the inner derivative equals 1. You might also use the first binomial formula to say this is x squared plus 2x plus 1, and then the classical derivative. It's the same result. You get 2x plus 2. Okay, anyway, so what can we do? We can simplify terms. We can cross out here the exponent of 2. Here we can cross out this factor of x plus 1 against one of these factors in the denominator by reducing the exponent from 4 to be 3. You see what I'm doing? I'm just crossing out one of these factors everywhere. What remains is, look here, it's x plus 1 minus 2x. Are you just removing these parentheses carefully? I hope you see it. What I get in the numerator here, it's x plus 1, and then minus multiplying 2, and minus 2x, and then minus 1 times 2, which means plus 2. And so in the end, actually, x minus 2x, it's negative x plus 3. And exchanging these, because then it looks a little bit nicer, I get 3 minus x. Actually, that's what it is. And this is nice because it also tells us that there must be a local extremum, sort of a turning point of this function where the first derivative gets 0. Quite obviously, if x equals 3, we have a 0 of the first derivative. And in fact, we have a local and even a global maximum of this function at x equals 3. And since it must be damped, since it must be approaching 0 at the outside, I even can conclude that there must be sort of an inclination point. Is it called inclination point, or is it called deflection point? I'm sorry, I don't know how it's called, where the second derivative equals 0. And this will be at x equals 5, as I found out, just for your info. It's called, I think it's really called inclination point. I'm not quite sure. A point where, you know, the curvature changes from, in this case, from a right-hand curve to a left-hand curve. You know what I mean? So that's quite interesting, but even more interesting is my rough sketch is not so bad, but it's not really exact neither. Look here, this is the plot generated with GeoGebra. It's very, I think it's very impressive that here you see our absolute maximum, which by the way equals 1/8, isn't it? Look here, inserting x equals 3. In this term, we get 3 minus 1 is equals 2 here, and then 3 plus 1 equals 4. 4 squared equals 16. So we get 2/16 shortened. This is equal to 1/8. And this is rather little, but whatever, it's the maximum value of this function. And it almost seems to be a horizontal line, right? So it's a very flat curve around the maximum, but it still is a maximum here at x equals 3. So there must be, but I've never seen it before, such a flat curve with a maximum. Anyway, it's interesting. Here you see the pole at -1 with no signature change, and so on. And you would see, with an extended view, you would see this point of inflection. I think, yeah, that's it, inflection point. I think that's the term at x equals 5, where this decrease changes to such a way that it approaches 0 in the end. Well, that's some details around this function, very interesting. But now we have almost solved our problem, because we just have to insert the 0, which is at x equals 1, into the first derivative, so that we get the slope at this position, and then f prime of 1 will be 3 minus 1 here, and then over 1 plus 1 cubed. So we get 2 and 2/8, as you see, 2 power 3 equals 8. So 2/8 shortened equals 1/4, and 1/4 is the slope of this tangent here, so that the inclination angle alpha will be the arctangent of this value of 1/4. This is just a little addition standard formula. This is around 14 degrees in the classical degree measure. Okay, so it's relatively flat. Sorry for this extended explanation.